Hello, this is Lance, and here is our final demo for our monkey tracker. Our group consists of 3 ECE members, which is Joseph, Nathan, and I, and 1 CPE member being Evan. We hope you found our project to be interesting, so let's get right to it.
Hello, my name is Joseph and I'm an electrical engineer on this project, mainly in charge of the PCB tracker. The following recordings constitute our final demo video and consist of various tests we've performed with our devices over the last few weeks. As you know from our paper, our PCB had power issues but was showing promise as we continued to work on improving them. Unfortunately, it was damaged before we were able to fully incorporate it in a complete system showcase. Because of this, our videos are split into two main categories. The first category is video assessing the PCB performance before it was damaged. The second category of videos is the full system analysis, which was performed with a breadboarded substitute for the full tracker PCB. This substitute is a good representative of the PCB's hardware capabilities because it uses the same microcontroller, radio, and GPS units. The breadboarded substitute features a GPS breakout that our team designed. The presentation will begin with showcasing our system's ability to meet three key design specifications, which are GPS accuracy, radio range, and system affordability. After this, the PCB tracker's capabilities will be shown with the video taken before the damages. This video will show the tracker's ability to send radio signals and acquire GPS location with an external GPS module. After this, there will be a power and signals analysis where tracker and base station values will be discussed. Following this will be the full system demonstration using the breadboarded substitute, where the system will be shown to receive GPS coordinates from our tracker via radio and relay these over web post transmissions. The final section will be a presentation of the challenges that we faced during the project.
Our first requirement specification that we have achieved is average GPS location accuracy within 15 meters. Initially, we tested our GPS, the ORG1411 in Blanchard Park, and used a cell phone's GPS coordinates provided by an online website as reference. We quickly discovered that the cell phone's GPS values were not accurate at all. We witnessed errors ranging from 100 meters up to 470 meters and knew the phone GPS was the inaccurate ping by scoping out landmarks or shapes on Google Maps. We redid the test using landmarks as references. The image displayed has various red dots where we stood with the GPS running. This image shows how we measured the error distance from actual position to GPS coordinate position. The white dot is the actual location and the red marker is the GPS location. Here is a quick demo of the process and obtaining a fix at the location shown in the previous image. Here's the breadboard. You can see the Adafruit feathers connected to our custom GPS breakout along with a few resistors and an LED. We plug in the tracker and the code that was previously flashed onto it will automatically run when powered on. We make sure that the serial port is connected and the correct board is selected in the Arduino tools settings before opening the serial monitor. In the serial monitor, we see that the GPS is running and querying for a connection involving at least 4 satellites for trilateration. We don't immediately have a fix, but in just a few seconds, we already have time. This means that the GPS has already established a connection with at least 1 satellite. Normally, time acquisition and constant updates of time at a rate that mirrors real time indicates that the GPS will soon obtain a fix. We obtained a fix. Here we can see latitude, longitude, time of acquisition, and IDs.
The second requirement specification is radio transmission range. Our minimum requirement was to cover a 0.1 kilometers squared area with an optimal of 0.2 kilometers squared. This corresponds to a minimum distance of 223 meters radially and an optimum of 316 meters. Prior testing with slightly different units to those shown in the footage was able to reach up to 400 meters in wooded terrain. This footage utilizes our breadboarded PCB substitute and the base station and achieved upwards of 250 meters of range. Given the results of all the radio testing we've done throughout the project, we feel confident saying we have reached the 223 meter minimum requirement.
The final requirement specification met is budget, where the total system cost should be less than $2,400. The current system, involving VHF telemetry and manual tracking of the cotton-top tamarins, costs between $2,400 and $3,000. We are tasked with creating a cheaper system, and our total cost meets this requirement specification comfortably. The total cost of the base station system hardware and 6 backpack trackers is approximately $1,332 plus $3 a month for the cellular data plan. This value excludes the cost for the mechanical team's housings, as well as any application cost that the CS team may have, but the base cost for the hardware is significantly lower than the low end of $2,400, and we feel confident that this requirement specification has been met. No demo will be displayed for this part.
This video clip shows us opening a serial terminal with the Arduino Uno operating as a radio receiver. The Uno is running basic receiver test code, where it listens to see if any devices nearby are sending radio transmissions. We can see that when we plug in the battery to power the PCB, the serial terminal begins reading its radio transmissions. This test shows that although the PCB never managed to get full onboard power, it was still able to send radio transmissions successfully. This video shows two key points. One is that although the PCB does not want to power onboard devices up to 100 milliamps, it can do so for external devices. This is shown because the PCB is powering the external GPS perfectly capably, as indicated by the green on light. This footage also shows that the PCB can get GPS fixes using the external module, as is shown in the serial terminal text.
After further analysis of the PCB files and looking at the traces, we tested the supply current of the tracker to find the current to be roughly 80 milliamps, which was a significant improvement to the 17 milliamps from the PCB tracker after assembly. However, it still did not fix our initial problem of acquiring a GPS fix. Using an oscilloscope, we tried to compare the waveforms of the tracker, which is yellow, to our breadboarded tracker, which is green. We probed different power traces within the components to see any deviations from the breadboarded tracker or if one component is too noisy. Unfortunately, both seem to have a stable supply voltage output in the figure below. However, when we measured the data lines for both trackers, we later found out that the PCB tracker was displaying an unusual sinusoidal waveform behavior not seen in the breadboard tracker. In the breadboarded tracker, we see a steady waveform with minimal noise, and if we were to enhance the waveform, we can actually see that it displays a square wave. This observation makes us believe that there could be problems in the PCB tracker's data lines, which interferes with the GPS fix, even though we were able to get a GPS time when we tested our PCB tracker previously in the video. This chart represents the output voltage over time of the Arduino Uno and for the SIM76 GSM Shield during a 24-hour period. In the Arduino Uno, the graph shows that there is an initial decrease from early in the morning, then jumps back around the afternoon, and then decreases during the night. If these results are accurate, that means that it can effectively sustain enough power for the Arduino Uno to last a week and maybe a year. For the SIM7600 GSM Shield, it displays similar behavior but decays a lot faster than the Arduino Uno's voltage over time, which is to be expected as there is only a diode present for the solar panel to regulate the current flow. It is not as efficient as the DF Robot Solar Charger controller.
This is where we filmed the entire tracking system in action. As you can see on the table, there is the base station with its solar panels and the multiple trackers. Right now, we are seeing the radio transmission that was sent from the tracker to the base station in the serial terminal. Then the base station, once it receives the transmission, it tries to upload the data from the tracker to the website using cellular data. The screen we are seeing right now is the logs from the website that show the successful transmission from the base station to the website.
The cell module sends data through data sessions controlled by the Arduino Uno. Here we manually enter add commands into the serial terminal and attempt a web post to the computer science team's website. As you can see here in the list logs, the server has successfully received the message. Here is the base station, the cell module is connected to wall power, and the Arduino is connected to a laptop. This laptop shows the serial terminal displaying radio reception and data session status. This laptop shows the data received by the server posted from the base station. Here is the breadboarded tracker used in the GPS demo. Joseph moves into position right outside of HEC to get a GPS fix. While Joseph waits outside to obtain a GPS fix, the base station queries for GPS coordinates transmitted through radio. A data session is initialized immediately after a radio transmission has been detected. Every new line after the data initialization indicates the status of the web post. Here is the transmission data successfully posted. After parsing the GPS data, we input the data into Google Maps to measure accuracy. The results were a 9-meter deviation.
The first hardware challenge we faced as a team was the part sizes on the PCB. Since the part sizes were required to be small, we wanted to get the smallest parts that we could get our hands on, which at the time a lot of these parts we wanted were out of stock because of the pandemic. We had to improvise and get slightly bigger parts, unfortunately. Also, since the parts were extremely small, we were required to get an expert to solder the major parts on the PCB for us, which were the GPS, the radio transceiver, and the CPU. The other challenge we had was figuring out why our PCB didn't work when we tried testing the GPS on it. What we found out was that there was a resistor that was creating a short because of the small internal resistance it had. The last challenge we had was testing the different components on the board. This was a challenging task because the components were so small it was hard for us to be able to use the oscilloscope to fully test them, because the probes were a little too big to get to the components. The main software challenge we had with the tracker was with the sleep mode. The sleep mode on the tracker had problems because when the tracker would go to sleep, the serial terminal would disconnect and would not reconnect when it woke up from sleep mode. So we had to improvise while testing. So we used a radio receiver to test if the tracker was working properly. The way we did this was to have the radio transceiver on the tracker to send the data we needed to the receiver, which was hooked up to a different serial terminal, and from there we could see the data we wanted to test. The other software challenge we had was the connection between the base station and the CS team's website. The reason why the connection is unreliable is because sometimes the base station will fail to upload the data to the database on the website. The reason why is because the signal is sometimes not strong enough, which will cause the upload to time out. The last challenge we had for software was working with the cellular data. This was a big issue because at the start we tried to work with 2G, but then realized in Florida it has been mostly discontinued. When we figured that out, we went with 3G, which then worked, but at the same time we still experienced some places where the base station will still sometimes not get a strong enough signal to send out the data to the website. This here concludes the final demo for the monkey tracking project. Thanks for watching and have a nice day.